This one's one of my favourite chapters. Analysis of organic compounds, unlike last chapter, inorganic. Okay, so we're dealing with carbon, hydrogen, and oxygen, a little bit of nitrogen and stuff, bonded in large molecules. Oh, what a great start. So here's our inquiry question. How is information about the reactivity and structure of organic compounds obtained? So we're looking mainly at the structure, determining the structure of organic compounds. Alright, what have I written here? Let's see what I've rambled on about. The analysis for organic compounds, probably of, I meant there, is important for many reasons. Some organics are toxic, and so environmental samples may need to be analysed. The ability to take a sample that is a mixture and have an instrument both qualitatively and quantitatively analyse is very attractive. Okay, so getting a sample, finding out what's in there and how much, hugely important. Many pharmaceuticals are being developed from obscure biological sources. Okay, so we're finding molecules out there that do some, going to use technical words here, medicine-y type stuff that are made by living organisms. We want to make it in a large scale in the lab. Okay, so using these type of instruments that we're going to learn about, we can identify the structure of this molecule, and organic chemists can make up a series of steps to synthesize, is the word that I'm looking for, synthesize these products. Okay, they can also, these instruments, analyze the yield at each stage of these reactions, so how good and how much we're getting, and ensure that we've got the correct product that we're looking for and not some other kind of like side product that's going to poison and kill us. Okay, and so that they can and have removed any dangerous byproducts, as I just said there. Okay, so first up we're going to we're going to talk about chemical tests for functional groups. Okay, we've already talked about this. This is a bit of a revision in this first chapter. In this first video of the first chapter. All we need to do, the syllabus is talking about what do we do when we want to find carbon-carbon double bonds, hydroxyl groups, and carboxylic acids. We've done all this, okay, in the last module. So here's a nice summary table, okay, but here is a bit more visual, which I like. So testing for double or triple carbon-to-carbon bonds using bromine or bromine water, okay. So you've got your unknown sample, you've got the brown bromine water, you drop it in, and the brown decolorizes, okay, if it's got a double bond there, okay. So if it's unsaturated, double bond or triple bond, it's going to decolorize the brown color of bromine water. Now I've just put bromine water as Br2 and adding a Br and Br across the double bond. We know that because it's in solution, the water is going to interfere with it, and we know it actually goes to this guy instead. But the HSC, for some reason, they'll still mark you correct for this to keep it simple, okay? So don't worry too much about that. Okay, so if you have a saturated single bond there, bromine water in there, you get no reaction happening. You get an unreacted bromine water layer there, okay? Now remember, if you expose this to UV over a long time, you'll get a substitution reaction, but we're talking about immediate results here, okay? So for your unsaturated, dropping bromine water in will decolorize it, so you'll get a decolorized aqueous layer and then an organic layer above it. But if you drop it into your saturated one, you're going to get the two layers, but you're still going to remain that brown color. All right. Now, we didn't do that one in the lab because bromine water is slightly toxic. What we did was use potassium permanganate instead. This one, different addition reaction across the double bond, and it's good because it starts off that bright purple, and if it's a successful reaction it goes clear, but sometimes you might get a brown precipitate, and I should show that there, shouldn't I? You might get a little bit of brown precipitate, which is the manganese dioxide. Okay, sometimes you might see that. So here we've got our double or triple bond, we're going to drop the purple into it, and we see the purple disappear, okay? We still get the two immiscible layers, the organic layer that has your organic compound in, and you get the water aqueous layer that originated with a permanganate solution, okay? And you'll get the brown there. Now, if you have your saturated molecule, what's going to happen is you'll drop your purple solution in. It will sit on the bottom unreacted as purple, okay? Remember when we did it too, you might need to give the test tube a bit of a shake to make it really work. But yeah, the potassium permanganate, a lot safer to use. Okay, a couple of videos if you choose to watch them. Alright, so the next one is testing for alcohols. So here we're going back to using potassium permanganate again, the oxidation of alcohols, okay? So using potassium permanganate to oxidize alcohols, and remember a primary alcohol will oxidize to form first aldehyde and then all the way to a carboxylic acid. So a primary alcohol will decolorize potassium permanganate because it produces carboxylic acid. A secondary alcohol, because that alcohol is not on the end of the molecule, it will only oxidize to a ketone. So again, it will decolorize potassium permanganate. Now a tertiary alcohol will not decolorize, and what you'll end up is a lighter purple solution. You could get 2 layers depending on the alcohol, but just say it doesn't decolorize, okay? Alright, another thing that you can test, alcohols will react with carboxylic acids to form esters, okay? So to test whether you've got an alcohol, you can mix it with a certain carboxylic acid, put in a few drops of your concentrated sulfuric acid, do the reflux, and you got a lovely smelly molecule there. She seems quite happy about what she's smelling, so it's not one of the gross ones. Okay, also, here's a new one that we didn't talk about before. Primary, secondary, and tertiary alcohols react with sodium metal to form an alkoxide anion and hydrogen gas, okay? It's a very similar reaction to between water and sodium, but it's less vigorous, okay? So here we've got an alcohol, so our R group alcohol on the end, and we're adding on sodium metal, and we get, it turns it into an ion, okay? So it gets it forming an ion, so it loses the H off there, and the sodium becomes oxidized, and you get hydrogen gas coming off, okay? So for example, here I've got ethanol and sodium. It forms the ethoxide ion in solution, and also the sodium ion, so the sodium gets oxidized. So you form in solution, you could put that as one formula of sodium ethoxide, okay? And you've also got hydrogen gas coming off. Since we've got a solution and a gas coming off, a lot of bubbles, okay? And one thing you know, if you want to contrast it, we've seen the sodium and water experiment where you put it in, it gets quite hot. It's a very exothermic and vigorous reaction there. Lots of bubbles are formed, and you may see sparks, okay? Contrasting it with a primary alcohol, you get slightly less bubbling, and it's not quite so energetically vigorous, okay? But still a lot of bubbling. If you do a secondary alcohol, it's less bubbling. If you do a tertiary alcohol, it's even less, okay? So you can use sodium to make sure you've got an alcohol, and you can, if you've got some like other alcohols handy, a primary, secondary, and tertiary, you can even compare it to other primary, secondary, and tertiary reactions to kind of have a good guess about whether it is your unknown one is primary, secondary, or tertiary. So that's a nice handy one. Alright, I think it's the last bit here. We need to test for a carboxylic acid. So remember the carboxylic acids, if you've got organics and you want to test for a carboxylic acid, the best thing to do is test whether it's an acid. Best thing to test whether an acid, blue litmus paper, does it turn red? Okay, you can also use a universal indicator if you want to. Another thing that you can do is it's going to react with carbonate to produce bubbles, okay? So you can have your potential carboxylic acid there, you put some solid sodium carbonate or sodium bicarbonate in there, and you produce carbon bubbles. You can test those bubbles too seeing if they extinguish a flame, bubbling it through lime water to make sure it's carbon dioxide as well. Okay, so there's some common tests for carboxylic acids. All right, we've got a past paper question here. An organic liquid was tested using the following method. So first, 2 drops of bromine water are added to 5 ml of the organic. So they're doing bromine water, so they're testing for saturation. Okay, so after that, 1 drop of the organic was added to some water and stirred. So they're testing for solubility is the word that I'm looking for. Solubility. And then the pH of the solution. And then, so they're testing the pH, of course. Okay, so the results were bromine water did not change color. Okay, so it must have mean that it was saturated. I've lost my pen there. So it's a saturated organic. It was added to water and dissolved, so it must be a small polar organic. Yeah, it can't have too long of a carbon chain there because it won't dissolve in water. And its pH is quite acidic. So it's a carboxylic acid. So I'd say it's a small polar carboxylic acid that's saturated. All right, ethanoic acid. It's a carboxylic acid. It's small and polar, and it's saturated. It's got a carbon-to-carbon single bond. Yeah. That's looking really good. Okay, let's just check the other one. Ethylene is the same name as ethene. Well, it would change color with brown because bromine would add across it, so it doesn't fit that. It wouldn't really dissolve in water because it's non-polar, and its pH wouldn't be at 3. It'll be fairly neutral, so no, it's not. It's not ethene or ethylene. Ethanol, okay, ethan, it's got a carbon-to-carbon single bond. It wouldn't change. Sorry, it did not change. Oh, so that one's good. Okay, so that's not going to change bromine water. Ethanol dissolves in water, yeah, because what muggles call alcohol. pH of ethanol and alcohols, though, are just under 7. So at a guess, between 6.5 and 7.0. So it's not that pH too high. Okay, the pH of ethanol will be too high. Pentane, okay, again, it's saturated. Pentane will start not dissolving on water, yeah? It's not polar enough. And the pH of it's no. We've got ethanoic acid there because it's a saturated, small molecule that's polar, and it's an acid as well because look at the pH. All right, there's some questions from the textbook, and I'll see you next video.